All right. Um, I don't know why. So last time we just introduced vectors in two-dimensional space in XY plane. Um, that's chapter 11, section 1. So we're going to do section 2 today. We're going to extend the vectors in 3 dimensions. So that's called space coordinates and the vectors in spaces. Okay, how do we use vectors in dimensional space? And everything is just a natural generalization in two-dimensional space. And you might have learned this before. So just give some review on it. So just like in 2D space on the plane, in the three-dimensional space, we also have coordinates. This time we just introduce one more uh, degree of freedom. So um, you know you will need three numbers in the order triple, not pair. Okay. Um, and we call the x, y, and z coordinates. Okay. Um, and then we got all kinds of x, y plane, y, z plane, and x, z plane. Um, just like you know, in the house, you have the floor and the two walls, and all those three types of planes are orthogonal or perpendicular to each other. And if you try to draw those three types of planes, the xy plane, yz plane, xz planes, and they know, orthogonal to each other, just like we show in the graph below. And then those planes, if you extend all of those three types of planes, they will divide the whole space, the 3D space, into octanes. Okay, we don't call them quadrants, we call them octanes. There are 8 of them if you think about it. You know, each time you cut, you just divide the space by half. So if you do it 3 times, then it becomes 8 pieces. 2 times 2 times 2. Each piece is called the octanes. Okay. And the important thing is the three-dimensional coordinate system is a right-hand system. That means when you draw the x, y, and z axis, they follow the right-hand rule. All right. Uh, so so if x is pointing to us from the uh, plane or the paper plane, and the y is on the paper plane to the right, the positive y direction, and the positive z direction is pointing up on the plane. Then you can use right hand um, to describe this coordinate system. All right, so you can point your thumb of right hand to the positive z direction, and then you curve it, curl it from positive x-axis to the positive y-axis. You know, so that gives you a right hand system, and then the coordinates of any point in the 3D space, x, y, z are defined um, from the point to the x, y, y, z, and xz planes. All right. So, for example, if you draw a line uh, perpendicular to the yz plane or parallel to the x-axis, then you will get the x coordinate. All right. And if you draw a parallel line to the y-axis and it intersects the xz plane at some point, then you get the y coordinate. Okay, the length. And you draw a perpendicular line to the xy plane, then that gives you the z coordinate. Okay, so that's how the coordinates are defined in the 3D space. All right, so let's just do one simple example how we draw a lot of points in the three-dimensional coordinate system. So suppose we have a point with coordinates 3, -2, and 5. So what you do, you can start from the origin, move 3 units along the positive x direction, and then you move 2 units opposite to the positive y direction or negative y direction, that means. And then you move 5 units up parallel to the positive z direction, just like this. Okay, so you can see the what the box, right? So that's pretty straight. Okay, in 3D space we also have the distance meter, pretty much like in two-dimensional space. We got x1 minus x2 squared, or x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Take the square root, where x1, y1, z1 are the coordinates of one point p1, and x2, y2, z2 are the coordinates of another point p2 in space. Okay, so you just get another part for the z components. And similarly, the midpoint p of those 2 points, p1 and p2, is just the average of the coordinate components. So the x coordinate of the midpoint will be x1 plus x2 over 2. The y coordinate of the midpoint will be y1 plus y2 over 2, and the midpoint z coordinate will be z1 plus z2 over 2. All right. So again, you just introduce another component in z. So for example, if you want to find the distance between the 2 points p1, -2, 3, 2, and p2, 2, -5, -2, you just subtract the components of the 2 points individually and square and add them up and take the root. So you get 2 minus -2 squared, so that's x2 minus x1. -5 minus 3 squared, that's y2 minus y1 squared. And then -2 minus 2, so that's z2 minus z1 squared. Okay, so 2 minus -2 is just 2 plus 2, so I get 4. 4 squared is 16. -5 minus 3 is -8. -8 squared is 64. -2 minus 2 is -4. -4 squared is 16. So then you just add those numbers together. You're going to get 96. 16 plus 64 plus 16. Okay, that's easy to do. And then you can simplify this a little bit by factoring 96 into 16 times 6. And then you take the root of 16, you get 4. So the final answer will be 4 times square root of 6. That's the distance between the 2 points. You can also find the midpoint of 2 points easily by using the formula given here. So here we got 2 points p1, 4, 0, -6, and the p2, 8, 8, 20. So we want to find the midpoint of those 2 points. So we just take the average of the components of the coordinates of these 2 points. So that's 4 plus 8 over 2, 0 plus 8 over 2, negative 6 plus 20 over 2. So x1 plus x2 over 2, y1 plus y2 over 2, z1 plus z2 over 2. Okay. So 4 plus 8 is 12, 12 over 2 is 6. 0 plus 8 is 8, 8 over 2 is 4. Negative 6 plus 20 is 14, 14 over 2 is 7. Okay. So this is the midpoint of those 2 points. So one thing, although these are pretty straight, there are simple formulas, don't mess up the distance formula and the midpoint formula. Okay. One second. Now let's talk about a sphere in space. All right. So in the three-dimensional space, we are talking about a sphere inside of a circle, and everybody knows what the sphere is. Basketball. Okay, that's a sphere. So it has a center and a radius. So the center will be at x0, y0, z0. Those are the coordinates of the center of the sphere, and then it has a radius. And then the standard equation of the sphere will be x minus x0 squared plus y minus y0 squared plus z minus z0 squared equal to r squared. Okay, so that means for any point on the sphere with coordinates x, y, z, it has to satisfy this equation. All right. So make sure you know what it means by those variables in here. So, for example, how do we find the equation of the sphere of radius 5 and the center at that point 4, negative 1, 1? Just plug in numbers, x0 equal to 4, y0 equal to negative 1, z0 equal to 1, the r equal to 5. So then we get x minus x0, which is x minus 4 squared, and then y minus y0 squared, so you get y minus negative 1 squared, and z minus z0 squared, so that's just 1 squared, equal to 5 squared, r squared, okay? And y minus negative 1 is just y plus 1, the 5 squared is 25, so we get the x minus 4 squared plus y plus 1 squared plus z minus 1 squared equal to 25. So that's the equation of the sphere in the any questions? No question. Okay, so now we discuss the points in 3D space. Let's talk about the vectors in three-dimensional space. So again, now we have 3 components for the vector instead of 2. So we can call those 3 components of vector v to be v1, v2, and v3, and we can also write this vector in terms of the standard units. Okay, j and k. So those I, j, and k are the unit vectors in the x and z axis. If you write the components of I, j, k themselves, then I will be 1, 0, 0, j will be 0, 1, 0, k will be 0, 0, 1. Okay, so as shown in the graph below, the red vectors. So there are unit vectors in the 3 axes. So then you can write vector v as v1i plus v2j plus v3k. And then the 0 vector in here will be all zeros for the components. So it will be 0, 0, 0. Okay. Just like we did in two-dimensional space, we can also draw any vector from between 2 points. So suppose there are 2 points P and Q in this space, then we can draw a vector from P to Q, and P will be the initial point, and Q will be the terminal point. And then the vector PQ, denoted by PQ with an arrow on the head. It will have components Q1 minus P1, Q2 minus P2, and Q3 minus P3. So again, we just subtract the components of those two vectors and 2 points, terminal minus initial. All right. Okay, so we have a bunch of properties for the vectors, like in two-dimensional case. These are just the very parallel with two-dimensional case. So suppose we got two vectors u and v with components u1, u2, u3 for u, and v1, v2, v3 for v. Let's say c is a constant or a number. Okay. It doesn't have to be always a constant, but a number, a scalar. All right, it's not a vector. And so if we say two vectors are equal, u and v are equal, that means the components are equal. So u1 equals v1, u equals v2, and u3 equals v3. And the length of vector u is just the square root of u1 squared plus u2 squared plus u3 squared. Just like the distance formula, right? You just add the one component in here, u3 squared, from the length of two-dimensional vectors. Okay, and the notation is the same. You put two vertical bars, okay, on u. Okay, and then the unit vector in the direction of u, as we discussed before, is just the vector u itself divided by the length of u. All right. So, if you divide the vector by length of it itself, then it becomes a unit vector. Okay. So if you write vector u in component form, then you get 1 over length u times u1, u2, u3. Okay, of course, we're not talking about the zero vector here. Okay, you cannot divide by 0. And u1 plus u plus v vectors add together, just add the components separately. So u1 plus v1, u2 plus v2, and u3 plus v3. You can also multiply c with the vector u by distributing the number c to the components of u. So let's just see u1, cu2, cu3. Okay, that's a very simple rules, similar to what? To vectors in two-dimensional space. Okay. So let's just do some examples. Suppose there's a vector PQ where P has the coordinates 4, -5, 2, and Q, the terminal point, has coordinates -1, 7, and -3. So P is the initial point and Q is the terminal point. So let's find the unit vector non-PQ. Okay, so this problem can be done in 2 steps. First, we can find the PQ. We just find the unit vector non-PQ by dividing vector PQ by the length of PQ, right? So to find the vector PQ, you just subtract the coordinates of Q and P. Okay, so the coordinate for Q minus coordinates of P, components by components. Okay, so that'll be -1 minus 4, 7 minus -5, -3 minus 2. Okay, be careful about this signs. -1 minus 4 is -5. 4 minus -5 is 7 plus 5 there. That's 12. -3 minus 2 is -5. So that's vector PQ, the components. So and then the next step, we can find the length of PQ easy by using the formula. So what you do is just take a square root of the sum of the squares of the components of vector PQ. So that's the -5 squared plus 12 squared plus -5 squared, take the root. So we get 25 from -5 squared and 144 from 12 squared and 25 again from -5 squared. You add them, you're going to get the 194. So the length of PQ is square root 194. All right. And there's not much you can do about it by, simplifying it. So you can leave it as it is. So the unit vector non-PQ is just the vector PQ over length of PQ. So that's 1 over square root of 194 times the vector PQ, which is -5, 12, and -5. So that's the final answer. Any questions? And this will be acceptable, in many cases if you just leave the answer in this form. It is okay to have radicals at the denominator in many cases. In most cases, you would need to multiply this 1 over square root of 194 into each component. So you get -5 over square root 194, 12 over square root of 194, and -5 over square root 194. So that will be perfectly acceptable if you want to do one more step. And up to that point, you don't have to rationalize the denominator. Okay, I'm trying to tell you that. Any questions? I think this is pretty simple, so I'm not going to spend too much time on this, and let's do one example. Parallel vectors. Okay, although it is very simple, to describe two vectors in parallel. It is very useful, and we're going to use it later. Okay. So let's say there are two vectors u and v, and they're parallel. How do you know they're parallel? Very simple. U is equal to some constant c times v, right? So c here is indeed a constant. Okay. So you can see what you do is just you change the length of the vector. When you multiply c to v, you just change the length, from v to cv, and the vector direction is not changed. So these two vectors are parallel, right? So let's say we have two vectors, z1 equals 1/2 I minus 2/3 j plus 3/4 k. So that's in the unit vectors components. And then there's another vector z2, which is -I plus 4/3j minus 3/2k. So we want to find the relation between this z1 and z2. In other words, are they parallel or are they perpendicular or neither? Okay. So we can try to do the problem by multiplying z1 with -2, for example. And there are different ways to do it. Okay. If you multiply -2 with z1, then you have to multiply -2 to each component of the Z1. Okay, so you just distribute -2 to each term in this component form in units of Z1. So -2 times half, you get -1, right? -2 times -2 over 3, you get 4 over 3. Two negatives make a positive, and you multiply 2 by 2, you get 4. And then -2 times 3 over 4, you get negative, okay? And you cancel 2 with 4, so you're still left with 2 in the denominator, so it's -3 over 2k. So we got -y plus 4 over 3j minus 3 over 2k. So guess what? If you compare this with Z2, they're exactly the same. So we just got the relation -2 times Z1 is just Z2. So in other words, these two vectors multiply each other, okay? And this -2 essentially means, you know, that the two vectors have opposite directions, okay? They point to opposite directions. Remember, vectors always have directions. So they point to opposite directions, but Z2 has the length 2 times the length of Z1. Okay, it's just enlarged by a factor of 2. So this Z1 Z2 are parallel. Sometimes you know, people call it the anti-parallel if they point into oppositions, but you can also call them parallel in general. So this is the example for last example in this section. Any questions for this section? No question. So let me just start the recording.